ahead, start recording. So we mentioned a little bit on Friday. Actually, that reminds me, I'm not sure if I posted the video from Friday. I might post it, I might not. It was a quick, like 15, 20-minute video, I think, anyway, because I wanted to give you guys time for the exams. And I'll probably try to give you guys more time on the future exams as well. I think most people finished pretty reasonably by like 1:30, and so that's fine. Like if most people are finishing around then naturally, I'm happy with giving you guys that time. So we talked a little bit about what a linear transformation is. Not sure how well you guys picked up on it. Of course, you guys were all anxiously waiting for the exam. So let's just kind of review our definition. So we want to study functions. Between vector spaces. In calculus, specifically Calc 3, you study what are called vector valued functions. So where you might have a function that maps for every given point in three-dimensional space, it attaches to that point some vector. These are vector fields that you study in Calc 3. The problem is that you do all sorts of differential calculus and pretty much any type of functions that we developed in pre-calc and calc 1, all your exponentials, your natural logs, your polynomials, a lot, like pretty much any of those can come up and define such a function. So for example, there are things like f of x, y, and z is equal to, and let's put it in our coordinate system. So let's use a column vector. So the x vector might be something like x squared times cosine of yz. The y formula might be natural log of x minus natural log of y. And then the z function could be z squared e to the 2xy. And this is really complicated. Well, I shouldn't say really complicated. It's fairly complicated. We would have to figure out, well, what all these functions define? How is this vector field changing? When is this vector field defined? At what points of x, y, z? But the problem is a lot of the differentiable structure measures rates of change. And second derivatives measures a notion of curvature. Right? Our differentiable, we measure all sorts of different curves. All of these functions, if we were to plot them in one dimensional, have different curvature, and then we've found different tangent lines and all sorts of stuff in calculus. So what we want to know is what type of functions are flat in some sense. I.e., preserve the structure of vector spaces. The surfaces we're on in Calc 3 and even in some of the lower calculuses, when we're looking at spheres, circles, parabolas, you know, they're twisted, they're curved, and we can use our calculus tools to measure that. But as we've seen so far in this course, all of the geometric spaces we're looking at are flat. I wish I could save that page of notes. I forget who asked, but asked for geometric examples and asked me to draw pictures, because I want to keep going back to that. It was a very good question. And when we drew it out, like, we saw lines through the origin are vector spaces. Planes through the origin are vector spaces. And that should kind of develop your intuition and notion of what a vector space is now in higher dimensions. Even if I have a 3-dimensional vector space sitting in a 5-dimensional region, it's still flat for what a 3-dimensional flat space can be. I can essentially define the space by a linear combination of basis vectors. Right? We have these basis vectors, which you want to think of as coordinate vectors. You know, how we can kind of draw a grid system based on our bases directions, and we're just going in straight lines. We're walking in straight lines along those bases directions. And so this is kind of what defines these flat spaces. And so the problem is if I start to curve things, just like if I define a circle or a parabola, we're essentially mapping, we're taking the R1, we're taking the x-axis, the straight line that defines the x-axis, and mapping it and curving it into a parabola or a circle or what have you. And so these complicated types of functions actually aren't going to work. And so let's try to arrive at what we need for a linear transformation. So our definition is a linear transformation let's call it T. It's going to map, let's just say, n-dimensional space to an m-dimensional space, is a function that, and I'll put this in quotes, preserves the linear structure of the vector space. So more formally, what should a linear transformation do? So what is our vector space? A vector space, we saw, it's really defined by a basis or a set of linearly independent vectors. And moreover, what are we doing with that set of linearly independent vectors? We are taking linear combinations. So, oops, sorry, V there. Linear combinations is this process by which we generate all the other points in the space. We can take scalar multiples of vectors, and then we can add all of those together. And so let's define what those are. So for any U and V that are n-dimensional vectors, and scalars S and T, if I apply a linear transformation to a linear combination, then that linear combination is, so to speak, preserved. In other words, we can perform the transformation on the vectors first, and then take the same linear combination. So here I have a linear combination of two vectors, v and u and v, where I take t times u plus s times v, then apply the transformation. That's going to be the same as performing the transformation on u, performing the transformation on v, and then from those vectors, doing the linear combination, namely multiplying the first by t, the second by s, and then adding them. And so now, through this definition, this is going to help us deduce, well, what types of functions can we actually have? What types of functions fit this model that will work well with our vector space structure that we have. So we saw an example on Friday where we said matrices are linear transformations. So if we have a matrix that is m by n, then what's that mean? It's got n columns. That means it can act on n-dimensional vectors by multiplication. So our AU exists. So running out of space here, but write that out. Our column or our rows are going to be A11 all the way up to A1n. And of course, that can now act on our vector U1 to UN. And moreover, by the properties of matrix multiplication, we know that if A acts on a linear combination of vectors, by the distribution property, I can distribute A over the sum and then by our properties of scalar multiplication, we can pull the scalar outside of the matrix multiplication. And so matrix multiplication gives us this exact property that we were looking for with linear transformations. Okay, so matrices are good. And we like matrices. It's just a square object with a bunch of numbers in it, right? No complicated functions, no sines, cosines, no strange derivatives, no derivative rules or anything like that. Just a bunch of numbers and some fancy multiplication we got to do. Of course, sometimes doing it mentally, the arithmetic, easy to make a brain mistake here and there, but conceptually easy to do. And so we have a theorem. Not only are matrices linear transformations, but all linear transformations specifically for finite dimensions are matrices. So proof outline. I'll go through it real quick. It might not make as much sense as if I do it rigorously or if we get too abstract with the proof. Examples will make it much more clear. So let's maybe outline the proof and kind of see what's going on here. And then we'll show some examples and do some computations and you'll see why this works. So pick our basis. Let's pick our standard basis. Which I'm simply going to denote just as the sum of EI from 1 to n. Yeah, for Rm. Right, so our EI are the vectors with zeros everywhere except a 1 in the ith position. Then, for each EI, and let me keep the vector sign over top of those guys, compute. We want to see where the linear transformation maps that. So again, a linear transformation is just a function. It's going to input an n-dimensional vector, output an m-dimensional vector. So T of EI is going to be, we will denote it A1I, A2I, all the way down to AMI. Then the matrix associated with T is given by, it's going to be the matrix of all of those. So A11, A12, up to A1n, A21, A22, A2n, all the way down to AM1, AM2, AMN. In other words, this first row this is T of E1. Each row is the image of the corresponding basis vector, elementary basis vector, under the linear transformation. Let's call this A. Sometimes, I think some books write it as like A sub T. Be careful with the T's, of course. With a superscript T, it means transpose. And so you can check, what's A acting on E1? Well, if we have 1, 0, 0, and zeros everywhere else, when we do the first row times the column, what are we going to get? We're going to get A11. Second row times the first column, we'll get A21. We'll keep going, and lastly, we're going to get AM1. And this is, by our construction, exactly where this linear transformation sends the first basis vector. So, what do we know? We know that this matrix is going to send each of the basis vectors to the same place that this linear transformation is going to send the basis vectors. And we know that matrix multiplication preserves the linear structure. It's going to respect linear combinations. So for any vector, so let's just write out, so we check that A acting on any of the basis vectors is going to be the same as the linear transformation acting on the basis vectors. And now for any V in Rn, we can write V as a linear combination of these basis vectors. And more importantly, this linear combination is unique. This is the only way we can write it. In other words, this V, I started to use T's as scalars. If we were to write it in a column vector, of course, each of these components, each of the scalars corresponds to the component in that respective position. And since both of these objects, both A and T, respect the process of linear combinations, I know that A acting on V is going to be A acting on that linear combination which we can distribute. That's going to be this here by our properties of matrix multiplication. So we're distributing the operation, the matrix multiplication over the addition, and then we're moving these scalars to the left. And now what do we know? If A acting on the basis vectors is the same as the transformation acting on the vectors, well, I can replace those with the transformation, and now we essentially play the same game in reverse. We can factor out the linear transformation. In other words, everything T does to any given vector, A is going to do the exact same thing. So since A acts in the same way on every single vector as T does, they are the same transformation. Let's see some more concrete examples. So we've got T of 1, 0, 0 is going to be 1, 2. T of 0, 1, 0 is going to be 9, negative 3. And T of 0, 0, 1 is going to equal 1, 1. And what do we want to find? Find the matrix A. Which will be a 2 by 3 matrix associated with t. And there's not much to these problems. Since we know where 1, 0, 0 goes, we know where 0, 1, 0 goes, and 0, 0, 3 goes, all we have to do is take the images of those vectors and make a matrix out of them. And specifically in that order. And that's all there is to it. So check on your own if you want to do a few of the calculations. What happens if I multiply this matrix on the right by the vector 1, 0, 0? Should be easy enough to kind of see that by matrix multiplication, it'll pick out this first column. Likewise, this one will pick out the second column. So the problems can get a little bit harder. So let's suppose we have a two-dimensional transformation. But the information we're given about this transformation is that t of 1, 1 is equal to 1, 2. And t of 0, negative 1 is equal to 3, 2. And again, we want to find the matrix A associated with t. So a little more complicated now. Let's look for easier points to start with. What do we need? We always want to figure out where t sends these standard bases. And so solving these in general is going to get a little complicated depending on what vectors we're given and what initial information we're given. Nicely enough, they don't make it too hard in this case, since we know that t of 0 minus 1 is equal to 3, 2. We know that t of 0 minus 1 is going to be equal to negative t of 0, 1. So we're just pulling the scalar multiplication of this vector 0, 1, negative 1 outside. And I know that this guy should have been equal to 3, 2. So we know now at least that t of 0, 1 is going to be minus 3, 2. Minus 3, minus 2. So that's our first piece. That'll be our second column. To find the first, well, we're going to have to use the other piece of information. So t of 1, 1 is going to be t acting on 1, 0 plus t acting on 0, 1. So all we're doing is breaking up the information that we've been given, the initial vectors that we were given, and breaking those up in terms of their linear combinations of our elementary, our standard bases. This right piece we know. This piece we don't know. So we're trying to find where the image of the vector 1, 0 goes. T of 0, 1 we now know is -3, -2. And now the image of 1, 1, we were also given the initial condition that it is overall 1, 2. And so now we can solve and determine where the image of this vector is. And so, of course, we just do the vector addition, and we get 4, 4. So now the matrix associated with T, we can just fill in our column. So 4, 4 is the image of the first one, and then the other one was -3, -2. So that is generally the process. This could be broken down, and it could be a little bit harder depending on the initial vectors they give us. They give us T of 1, 1. This could have been something like T of -2, -1. In which case, we would want to break those down in terms of linear combinations, and it would set up a system of a system of linear equations that we would again then have to solve in order to determine the images. Is that clear? Do you guys want to see an example of that? Let's see another method, because there's a lot of techniques that are going to be in here, especially once we have vectors that are not, if we're not given the images of these standard basis vectors. Just means we've got to do a little bit of work in order to find what those images are to solve for the columns of the matrix associated with that. So here's going to be our process. So if we are given a set of vectors which are linearly independent, with, if we make a matrix out of it, and we can take the inverse, and we know the image, so each of these A's, they're n by n, or they're in n-dimensional space, whereas the BI's should be in m-dimensional space. then how we want to find the matrix is going to be given by, let's see, so we want to put all of the B's in a matrix. And then you put the inverse of the A's to the right. So what you can kind of think of as, if I put the inverse of this matrix on the right, if I had all of the A's kind of listed out and multiplied on the right, well, it would cancel out this matrix here. And what we would be left with is the matrix of B's. So really what the transformation of T is doing is just kind of, if we did one column at a time, we would get the correct answer. So for example, let's do one in 3 dimensions. So we've got T of 1, 3, 1 is 0, 1, 1. T of 0, 1, 1 is 2, 1, 3. And T of 1, 1, 0 is 0, 0, 1. And so if we set this up, we want the image we want that to be B, the matrix associated with T. The problem is the information of how we got those images is that it didn't come from the image of our standard basis vectors. It came from the image of these other basis vectors. So what we need to do is we kind of want to think of, well, if these other basis vectors that we're acting on, sorry, I was looking at the wrong one, 0, 1, 1, and then 1, 1, 0. If we sort of undo this, in other words, since we can think of each of these vectors that we acted on, this 1, 3, 1, 0, 1, 1, 1, 1, 0, in some sense, those are the image of this matrix acting on the standard basis vectors. So if we want to undo that to get back to the standard basis vectors, we want to take our inverse. And so our goal is to compute our inverse first. So let's go ahead and compute our inverse. And let's get a new piece of paper. I don't think I have enough space for that. So we've got 1, 3, 1, 0, 1, 1, and 1, 1, 0. And since we're computing an inverse, we want to put an identity matrix on the right. And now what we are going to do is to row reduce this guy. And then the remaining matrix is going to be our inverse. So computing inverses of matrices, always a pain. Make sure you guys are familiar with this process. And let's see, which ones do we want to start with? I think keeping this guy on top is fine. And so let's go ahead and keep our first row. We're going to take -3 plus that guy. So we'll have 0, 1, and then -3 plus 1 gives us -2. We'll take negative row 1 plus row 2. I guess we should finish this row. So we'll have a -3 here, 1, 0. -1 times row 1 plus row 3, excuse me. -3 row 1 plus row 2. And we'll get a 0 there, of course, still have a 1 there, and then we'll have -1 from that column and -1 from that one, and 0 and a 1 left. Next, let's take row 2, so we need to eliminate that one. So we've got 1, 0, 0, -3, 1, 0. So then negative row 2 plus row 3 give us 0, 0. And then negative row 2 will give us +2 plus row 3 will give us a +1. That's nice. We won't have to do more work in that row. And then negative of that plus that gives us a 2, 0 and a 1. Negative row 2, missed a -1 there. So we're close. Now we've got to get rid of that -2. So we do 2 row 3 plus row 2. And I guess we can do row 1 at the same time. So let's do negative row 3 plus row 1. So that'll give us 1, 0, 0. If I do negative row 3 plus this top row, it'll give us a -1 there, a 1, and then a -1. Then let's see, some 2 row 3 plus that guy. So we've got 0, 1, 0, 2. That'll give us a 1 there. That'll give us a -1. And then a 2 here. Third row didn't change. And that's it. So now our T, or the matrix associated with T, let's go ahead and rewrite. So the B vectors, the images, were 0, 1, 1, 2, 1, 3, and 0, 0, 1. And then now the inverse we just computed, -1, 1, -1, 1, -2, or -1, 2, 2, -1, and 1. And then the last step is to just matrix multiply. So we do the first row, first column. It's going to be 2. First row, second column, minus 2. First row, third column gives us a 4. Second row, first column gives us minus 1 plus 1 plus 0. So that'll be a 0. Second row, second column, minus 1 plus 1, or 1 minus 1, 0. So another 0. Second row, third column, minus 1 plus 2 gives us 1. And last row, first column, negative 1 plus 3 plus 2 gives us 4. Last row, middle column, 1 minus 3 minus 1 gives us minus 3. And then last row, last column, negative 1, positive 6, and positive 1. So positive 6 there. And now, moment of truth. Did we do our algebra right? All the arithmetic. So our A we have as 2 minus 2, 4, 0, 0, 1, and 4 minus 3, 6. And so how do we check? So of course, this should be the matrix associated with T. We need to check the initial information, namely that T of 1, 3, 1 equals 0, 1, 1. Let's check 1, maybe 2 of them, make sure we get it right. And so what are we going to have? 2 minus 2, 4, 0, 0, 1, 4 minus 3, 6, acting on 1, 3, 1. And what are we going to get? So 2 times 1 is 2, negative 6 plus 4 gives us that 0. So 2 plus 4 minus 6. 0, 0, 1 times this vector will give us 0 plus 0 plus 1. That's good. And then 4 minus 3, 6. What's that going to give us? It's going to give us 4 minus 9 plus 6. So 4 minus 9, negative 5 plus 6 gives us 1. So that one works. Let's check one more. So we had 2 minus 2, 4, 0, 0, 1, 4 minus 3, 6. Acting on, let's do the third one, 1, 1, 0. This should give us 0, 0, 1. So let's check. So 2 minus 2, 4 gives us 2 minus 2 gives us 0. 0, 0, 1 times the vector gives us 0. And then here in the last one, we will have 4 minus 3 gives us 1. Good. So we did the computations right. Does that make sense? Does the process make sense? So that is going to be somewhat of a quicker algorithm, so to speak. In the first problem, it kind of generalizes that. The first problem, if you have vectors that are not the standard basis vectors that our transformation acts on, you can write those vectors in terms of a linear combination of the standard basis vectors. And then what you could do is use the properties of the linear transformation to come up with essentially a coefficient matrix to try to solve for it. But doing it that way might be a little more complicated, and you can essentially reduce the problem. Really, the key thing is now finding the inverse of those image vectors. Okay, so that's almost it for linear transformations. We do have quite a bit of time left, so I do want to use it. Let's try to do a couple more examples, and then we'll get a head start on some of the things we're going to talk about tomorrow. Let's see. Here's a good example. We want to let you just be the vector as 1, 2, 3. And let T be a map from R3 to R3, where T of V is going to be the projection onto U. So first thing we need to show that T is a linear transformation. And then 2, determine the matrix. So one of the things we need to do, let's pick another vector. So let's let our, not U, we want to use W and V be 3-dimensional vectors. And we note that T of W plus V is going to equal the projection onto U of this sum And so we need to show that this is linear. I don't think we've done this yet. So just by the definition of the projection, so remember it is computing the dot product of the argument vector with the projection vector divided by the norm of the projection vector squared. That's our scalar component in the direction of U. And so by the linearity of the dot product, we'll get our linearity out of the projection. So it at least distributes over addition. We also need to check scalar multiplication. I'll leave that a little bit more to you guys to spell out the details in a similar fashion. But if we have any scalar multiple of a given vector and we want to take the projection onto U of the scalar multiple of that vector, by the same properties, I can pull out scalars of the dot product, and following similar steps, you'll be able to show that this is just the same as pulling out the scalar from the linear projection or from the projection. So with those two things, you could show them both in one step if you want to use the definition and take linear combinations here, S of W plus T of V, and go through the whole process. Or you can show that a given definition for a transformation, show that it respects addition, or show that, and then separately show that it preserves scalar multiplication. And that shows linearity. So how do we determine the matrix? The matrix is going to be a little bit more complicated. What we want to figure out is where the images of our standard bases go. So for all of the three standard bases vectors, we need to figure out their images. So we'll just have to compute it. So T of E1 is just going to be the projection onto U of E1. And actually, let's keep it as EI. Maybe we'll be able to take us some shortcuts with some of these calculations so we don't have to do some of the same repeated steps every single time. Especially since we're computing the projection, let's go ahead and compute some of these pieces. And I guess if we want to write it out, this is going to be U dot EI over norm U squared in the direction of U. So let's go ahead and compute norm squared of U. So U is 1, 2, 3. So 1 squared plus 2 squared plus 3 squared. And I guess we don't need the square root since we're squaring it. So 9 plus 4 plus 1 is going to give us 14. We can compute each of the dot products individually. So U dot E1 is 1. U dot E2, 2. And U dot E3 is 3. And then we just have that U that we want to multiply by. So let's go ahead and write it out now. So our T of E1 is going to be 1 over 14 in the direction of U. T of E2 is going to be 2 over 14 in the direction of U. And then T of E3, 3 over 14 times 1, 2, 3. And so now we can essentially write down the matrix. We just got to do the multiplication. So the matrix associated with T of E1 is going to be 1 over 14, 2 over 14, and 3 over 14. T of E2, so we can simplify that. 2 over 14, 1 over 7, 1 over 7, 2 over 7, 3 over 7. And then T of E3, 3 over 14, 3 over 7. Let's go ahead and simplify that one. And then 9 over 14. Then if you want, you can simplify that guy too to 1 over 7. Any questions? Okay, so we've got about 20 minutes, 25 minutes. Let's see, where do we want to go from here? So we've got some extra time. Properties of linear transformations and special linear transformations. Let me take a look at the schedule and see what we got coming up. Yeah, properties, kernels of and isomorphisms, solutions to linear systems. Kernels and isomorphisms might be a little tricky to get into at the moment. I think we need to get into change of bases real quick. Okay. Let me organize my notes here. I'm just trying to see, going out of order in the book here, properties of linear transformations. I think we essentially defined S&T compositions. Yeah, actually, we've got quite a bit of time. Okay, that's kind of good. Maybe we'll get a little bit ahead over the next couple days or so, and that'll give us some more time for some of the other stuff. Some of these book properties and book chapters, sub chapters, I guess I should say, are a lot quicker than what was originally laid out on the schedule. So let's talk about alternate bases. So it's actually, in some ways, it's going to be easier. In other ways, it might be a little more harder than what we were just doing. Because what we just saw in some of those examples was that when we have a linear transformation acting on a linearly independent set of vectors, namely a basis, as long as I can invert that matrix or invert that set, when I make that set or those set of vectors into a matrix, we can sort of undo, so to speak, that portion of the transformation and then recover what the transformation looks like in terms of the standard bases. But sometimes we actually don't even need that step, because if we have an alternate basis or basis, then we can essentially define the linear transformation in the same way we would with the standard bases. So let's suppose we have some basis. V1 up to Vn. For Rn. Then for any vector x in Rn, we can write x as a linear combination of this basis. And moreover, this is unique. So notation that we will use, this set B is going to be our basis. And so we would write this that CB of x, or sometimes we write x as like a column vector, and we put maybe a B at the bottom of the column vector to indicate that our basis is possibly something different or given by these set that we have been given. And then essentially what we want to do is list those coefficients in our column vector. So for example, let's suppose we have our bases of 1, 0 and minus 1, 1. And we have our vector is equal to 3 minus 1. We want to find the expression for x relative to this basis. In other words, we want to find the linear combination that defines x. So what are we going to get? We're going to get a system of equations. So s times 1, 0 plus t times minus 1, 1 is going to be equal to 3, 1. And then we need to solve this. So it's pretty clear that t has to be 1 from the bottom column, bottom row. And then we will have s minus, since t is 1.
Shouldn't it be 3, negative 1?
Yeah, sorry. 3 minus 1. So our t is minus 1. And then, so we will get s plus 1 is equal to 3. And so our s equals 2. So in other words, our CB of x, find the order of your coordinates. So s was the first one. We do want to order the bases as well. So this is our V1 and this is our V2. So the coefficient corresponding to the first vector was 2, and then the other one's minus 1. And then we've got our bases, our change of bases in linear transformations. So maybe we'll do this in a couple steps. So suppose we have a basis and we'll call it B equal to V1 up to Vn. And moreover, relative to the standard basis, I'll just call this set E. We know the linear combinations. So I know that, let's say Vi is equal to, I'm going to change the scalars. Let's go ahead and use A's again. And so we're going to get, make sure I put the indices in the correct order. So Vi is going to be a column. So we're going to have, so we're going to have A1, I, E1 plus A, 2I, E2 plus A, Ni, En. Then the matrix A equal to, if we put all of those now in our matrix, I'm confusing my indices. A1, 2, and A, N1, A, row 1, N, excuse me, A, 2N, A, N1, and then ANN. Is called the change of basis. You call it a matrix, or you can even call it a transformation. From E to B. Now you can generalize this. Actually, we didn't need to have our standard bases here. This could have been a different bases. Could have been like U1 to UN. And as long as the linear combination, as long as those scalars are the same, we can kind of replace the EIs with whichever bases vectors we want. The matrix would still be the same. We would just have to make sure we are clear about which bases we are starting with. So in other words, what is this matrix going to do? The reason I use the standard bases is because when you're given a basis, you should in some sense kind of think of it, almost every basis can kind of be considered as a standard basis. Like we saw in the last example, here we just have a V1 and a V2. And so really what we showed was that X is just going to be 2V1 plus, minus 1V2. So X itself is a linear combination relative to V1 and V2. And now we're simply keeping track of that linear combination in our column vector. And so we might want to keep that subscript of B there down at the bottom to indicate that our bases was maybe a little non-standard. However, relative to B, the matrix element or the vector, column vector associated with V1 is just 1, 0. It is one copy of our first basis element. The column vector associated to V2 relative to the same basis that V2 defines, helps define, is 0, 1. It is the second basis element in that set. Does that make sense? So in some sense, these bases that we're choosing, even though we have this notion of a standard basis for Rn, no matter what basis we choose, as soon as we choose like one basis as kind of like the basis we're starting from, even if it's this basis, as long as we're clear relative to which basis we're working from, at least those basis elements with regards to themselves look very much like these standard bases. So in that regards, if we ever have higher dimensions, notice that I didn't use any of the properties of these standard bases here. So we could say we're non-standard. Because as soon as I have like a notion of a basis we're starting with, really what we're doing now is looking at, well, a different basis or a different set of vectors, and how do we arrive at those vectors in linear combinations of some given set of vectors in some terms of some given basis. And since that given basis relative to itself looks like the standard basis, we do essentially end up with the same thing. And so this kind of defines a linear transformation. And what you can check is that if I act A on any of the standard vectors EI, what are we going to get? We are going to get our column vector associated with that. So we're going to get, let's see, so our AI, it's going to be that column. So we're going to get A1I, A2I, and then down to ANI. In other words, A is a transformation that sends any given basis element from the initial basis to the corresponding basis element in our new basis. And so from this, essentially what we can do now is, now given any other basis, if we have a linear transformation defined between two vector spaces, in many ways it helps to initially define a basis. So we've been working with the standard bases, but as we were kind of just discussing, if we have a linear transformation or if we have a non-standard basis, well, at least relative to that basis, any basis looks standard. And so if we know how a linear transformation behaves on any basis, and now I have, say, a linear transformation, and we know how it acts on a specific set of vectors relative to that basis, we can essentially use that same process, the same process we did before, in terms of coming up with that linear transformation. Let me see if we can find a good example. Let's see. I'm not sure if we're going to be able to complete any of these examples with the remaining class time, since it does look a little computation heavy. So we'll formalize this a little bit more tomorrow. We'll talk more about how change of bases works and how we define these matrices associated to a change of bases, and then how we can apply those now with linear transformations. So if we have a linear transformation defined in terms of one basis, really what we can think of A as itself a linear transformation, but now from Rn to Rn, where this might have basis E, and then the basis we're choosing for now Rn in the image is going to be the basis E, basis B. So this will help us give composition. We actually do need to talk about some of the properties of matrices. So unfortunately, the order of the book kind of jumps around a little bit. So we'll start off tomorrow talking about properties of linear transformations. We'll demonstrate how composition of linear transformations really just boils down to matrix multiplication. And then now if we can understand these change of bases matrices as themselves linear transformations, it gives us a tool for transitioning any general linear transformation into any other form, depending on the basis we want to start with, or depending on what basis we want to change to. And all that's going to be done with matrix multiplication. So any questions on that? Okay, we'll explain more of that. We'll see examples with that tomorrow, but we only got a couple minutes and I got to get going. Office hours this week. Do you guys want to have office hours tonight? I can do Thursday again.